Hi guys, welcome back to the channel. In this video I'll be looking into buffers from the acid and bases topic from the A-level chemistry curriculum. I would advise you to be confident with the rest of the acid and bases topic before coming onto this video, so I'll link on the videos previously that we have done on acid and bases. So let's get started. So buffer solutions. The definition of a buffer solution is a solution which resists changes to pH when small amount of acid, base, or water is added. Adding water would be a dilution. Now it's important that you mention that it's small amount, because if you add a large amount, and the buffer will no longer be able to resist changes to pH, so it would no longer be a buffer. So it's small amount of acid, base, or water. So what makes up a buffer? So there's two types of buffer, and the first one being an acidic buffer. So an acidic buffer is made up of a weak acid, so it's a weak acid, not a strong acid, and the salt of that weak acid. So for example, looking at ethanol, so that's a weak acid. So ethanol and the salt of ethanol, which could be, for example, sodium ethanoate, it could be potassium ethanoate. So this could make up a buffer. And the other type is basic buffer. So this would be made up of a weak base and salt of that weak base. So for example, we might have ammonia and ammonium chloride. So this would make up a buffer. Now you need to be aware of how buffers work, and be looking at acidic buffers first. So the acidic buffers have a large reservoir of the weak acid, and they have the conjugate base of that weak acid. So the weak acid and the conjugate base would be in large amounts in the buffer solution, and we would refer to the acid as just HA, and the conjugate base of the acid as A minus. So for example, if our weak acid was ethanoic acid, so CH3COOH, our conjugate base would be CH3COO minus. Now earlier we looked at the composition of a acidic buffer, and we said it's made up of the weak acid and the salt of the weak acid. So when we're talking about the reservoir of acid and the conjugate base, so all of this acid is from the acid we were talking about, and all of this conjugate base is from the salt of that weak acid. So for example, when we looked at ethanoic acid, we had the salt as sodium ethanoate. So all of these conjugate base, CH3COO minus, would be from the sodium ethanoate which we had. So the sodium would be removed, and we would have just ethanoate ions left over. So what would happen if we added small amount of acid to our buffers? So adding acid would mean adding H+. And if H+ is added, what would happen is this H+ would react with the A minus, so with the conjugate base of that weak acid. So in this case it would be the ethanoate ions, and this would end up forming the weak acid itself. So we formed the weak acid, and the H+ ions would be removed. So why are we removing these H+ ions? So by removing these H+ ions, we're getting rid of the H+ ions, which could change the pH, because remember, pH is a measure of the concentration of H+ ions. So if the H+ ions would be removed, we would have the same amount of H+ as we originally had, so our pH would be constant. And when we're talking about it, what we say is that the ratio of HA to A minus remains constant. So I'm using the word constant, not the word same here. And if this remains constant, what this means is the pH remains constant. And this will become more clear when we go through a few examples. But now if we're looking at adding a base, so OH minus ions, now these OH minus would react with the weak acid itself. So when the OH minus would react with the weak acid, what would happen is the OH minus would end up gaining a hydrogen from that weak acid to form water, and we would have that conjugate base forming. So as you can see, we are again removing the OH minus from the system. So these OH minus wouldn't be reacting with the H plus ions which are in the solution, and because H plus ions are responsible for the pH, we wouldn't get a big change in pH occurring, because the concentration of H plus ions would be nearly the same as the original H plus ions. And again, the reasoning would be that ratio of HA to A minus remains constant, so pH remains constant. Now, the pH would not exactly be the same. There might be a slight change to the pH. Okay, so now on to how basic buffers work. So the basic buffers would contain a large reservoir of the weak base and the conjugate acid of that weak base. So the base we would be referring to as B, so this would be the weak base, and BH plus is the conjugate acid in this case. So if we again refer back to what we looked at earlier, so B could be NH3, and that would be our weak base, and the BH plus, so this would come from the salt of the weak base. So when we had the salt as NH4Cl, we could remove that Cl, and we would get the conjugate acid as being NH4 plus. So this would be our weak base. So what happens if we add acid to this weak base? So small amounts of acid. So adding acid again is adding H plus. So if we add H plus, then this will be neutralized by OH minus. So H plus plus OH minus would produce water. So looking at the reaction from the first equation, so we have H plus reacting with this OH minus, and this produces water. So we're getting more of the water. So the equilibrium wants to balance things out. So it would try to reduce the concentration of water by moving the equilibrium to the right hand side to oppose the change that's happened. So this would mean that more products would be formed, and this would end up forming more BH plus and OH minus, and we would replace the OH minus we lost by reacting that with H plus. But this is also gotten rid of H plus, and because if we get rid of H plus, there wouldn't be a change in pH, as the concentration of H plus is nearly the same as what we originally had. And again, for our reasoning, we would always say that the ratio of, so in this case it would be the base, the weak base, and the conjugate acid of that weak base. So the ratio of these remains constant. So the pH, I don't know why I've got BH plus there, but so the pH would also remain constant. So remember to keep using the word constant, don't use the word same. So what happens if we add base to this? So if we add base to this, we would be adding OH minus. So what would this do? So this would increase the concentration of the OH minus in the solution. So referring back to our original equation, so this means that the OH minus concentration increases. So because equilibrium always opposes a change, this would try and decrease the OH minus concentration by shifting the equilibrium over to the left. So we would be shifting equilibrium towards the left, so towards the reactant side. So the added OH minus would react with BH plus to form reactants. So remember that because we have a large reservoir of this B and BH plus, we can easily react the OH minus with that BH plus. So this is forming more of the B and H2O, and we end up getting rid of the OH minus that we added to this. So the OH minus can't react with the H plus, and the concentration of H plus would stay the same, nearly the same as the original concentration. So that's why the pH would also stay constant. So again, for the reasoning, what we would say at the end is that the ratio of B to BH plus, so B to BH plus, so the weak base to the conjugate acid of that weak base would remain constant. And so that's why the pH would remain constant. So remember this reasoning. So now looking at the buffer solution calculations. So first we'll be looking at what adding acid to that does. So luckily you do not need to know how to do buffer calculations with basic buffers. So this is only acidic buffers. So first looking at a question. So we've been asked to calculate the pH of a buffer which is formed when we add ethanoic acid. We've been given the pKa value to sodium ethanoate. Now for these type of questions we need three things to be able to calculate the concentration of hydrogen ions. From then we can calculate the pH. So the three things are the Ka value. For this question we've been given the pKa value, but we can get the Ka value from there. We need the weak acid concentration, and we also need the concentration of the conjugate base of that weak acid. So as we know, ethanoic acid dissociates, it partially dissociates into H plus, as well as the conjugate base of it, which is CH3COO minus, or any acid would dissociate into H plus and A minus. But for these type of questions we assume that there's been no dissociation that's occurred. So we only have the weak acid. We do not have any dissociation that's occurred. And the only conjugate base that we have, so CH3COO minus or any conjugate base that we have, is from the salt of that weak base. So we assume that all of the salt of the weak base has dissociated into A minus, and we end up getting A minus from there, and we do not get any A minus from ethanoic acid, even though we do end up getting some in reality, but in this case we just assume that we do not. So let's get started with the actual calculation. So first what we do is we would calculate the moles of the acid. So in this case it's 0.05, because remember to convert the centimeters cubed into decimeters cubed and times 1, and this would just give us 0.05. So this is the mole of acid, or the mole of, we can just say H plus because it's only a monoprotic acid, it's ethanoic acid. And then we will calculate the moles of that salt of the weak acid, which will all convert into ethanoate ions, or just A minus in any case, and this is also 0.05 times 1, which will also give us 0.05. Now I'm just going to write the dissociation equation down to help visualize things, and you don't really have to do that in an exam question. But so the ethanoic acid would just dissociate into H plus, and the ethanoate ion, so CH3COO minus, and we can get the Ka from there. So the Ka equation would just be so it's just reactants over products. So we have products over reactants, sorry. So that's CH3COO minus, and this would be over the reactant CH3COOH. Now for the next bit we could find the H plus concentration by rearranging this, but this bit's slightly different because usually all of these have been the concentration, but now we would sub in the moles of these instead of getting the concentrations. So this would be Ka and the moles of CH3 COOH over the moles of CH3 COO minus. So this is how it's slightly different. So I'm not going to sub in the concentration of these, but rather I'm going to sub in the moles of these. So to find Ka, I would just simply do 10 to the power of minus 4.76 multiplied by the moles of ethanoic acid, which I have calculated as 0.05, and then divide that by 0.05 as the moles of the sodium ethanoate, or it would be the ethanoate ions in this case. So this would get me 1.738 times 10 to the power of minus 5, and then I could minus log that, and this would get me my pH, which to 2 decimal places would be 4.76. So this is my acidic buffer, and if you're getting a pH higher than 7, then you know you've done something wrong, because that would mean that it would be an alkaline buffer instead of an acidic buffer. After this, they can ask you to calculate the new pH after adding either an acid or an alkali. So in this case, we're just looking at acid. So now they've added 10 centimeters cubed of 0.1 moles per decimeter cubed of HCl, which we know is a strong acid. So now for these type of questions, what we would do is first we would find the moles of the acid or the alkali that's been added. So in this case, it would be 0.01, which is the volume, so 0.01 decimeters cubed times 0.1, which would just be 1 times 10 to the power of minus 3. So this is the moles of HCl and also the moles of H+, because it's a monoprotic acid. So then to find the moles of acid and to find the moles of the ethanoate ions, what we need to realize is when we add an acid, the moles of the acid that we already had would increase. So this is when we're adding acid, because we are adding H+ ions, so we end up forming more of the HA, and the moles of the ethanoate ions we had, or the salt we had, will decrease when we're adding H+. So this needs to be taken into account. So what I would do is I would get the moles of the H+ that I originally had. So I can see the H+ moles there, and I can see the A- moles there. So what I would do is I would do 0.05, so the moles I originally had, plus 1 times 10 to the power of minus 3. And this would be the new moles of my acid. So this would be 0.051, and so I'm just going to write acid next to that, and then it would be 0.05, and I'm going to be minusing the moles now, because the moles of the ethanoate ions would have decreased. So this would just be 0.049. And now it's going to be the same over again. So I can use that same equation again. I don't need to write everything down again. So I can just say that H+, so now the new concentration of H+ would be 10 to the power of minus 4.76. Nothing's going to happen to the Ka value. And then it would be, what is it, 0.051. So because the moles of the acid goes on the top, and the moles of the ethanoate ions would go on the bottom, and we would get the concentration of H+, which becomes 1 0.81 times 10 to the power of minus 5, and if I minus log that to base 10, I would get the pH to 2 decimal places, the new pH being 4.74. So you can see that this isn't a big change. This is just a tiny change. I'm going to be looking at buffer calculations where we're adding alkali instead of an acid to it. So the question, again, it's asking me to calculate the pH, and it's given me the concentration of volume of the weak acid, the pKa, as well as the concentration and volume of the salt of the weak acid. So I would just first, as always, calculate the moles of the weak acid first. So 0.05 times by 0.1 in this case, so that would just be 5 times 10 to the power of minus 3, and then the moles of the salts. So this is just 0.03 times 1.50, and this would get me 0.045. So this is the moles of my acid and the moles of my salt. And now I'm just going to write down the equation for getting the concentration of H+, which would just be H+ is equal to Ka, and that's multiplied by the moles of so it's the moles of the acid. I'm just going to call it Hx in this case, and divided by the moles of the what is it called, the ethanoate ions in this case, because it's sodium ethanoate. So I'm just going to write moles of X minus. So now putting the values in, it would be H plus, so the concentration of H plus, Ka, I can just put 10 to the power of minus 4.68. So be careful if it's pKa or Ka. So if it was just Ka, I would just simply put in the value for Ka, but because it's pKa, I have to put in 10 to the power of minus 4.68, and then multiply them by the moles of the acid. That's just 5 times 10 to the power of minus 3 over the moles of the ethanoate ions. So this is just 0.045, and what I get as my concentration is 2.32 times 10 to the power of minus 6, and I would just simply minus log this concentration of H+, and I would get 5.63 as my pH to 2 decimal places. I hope the first bit is making sense now. So now moving on to the second bit. Now instead of adding an acid, we have added NaOH. So this is a base, and we've been given the concentration and volume. So again, what we would do is calculate the moles of the base we are adding and the moles of OH minus being added. I would just do 0.02 times 0.01, which would just be 2.10 to the power of minus 4 moles of OH minus. So this is being added, OH minus being added. So what you need to remember is when a base is being added, the moles or the concentration of the acid, the base, the sodium ethanoate or the salt would increase, and the concentration of the acid would decrease. So when a base is being added. So now adapting my moles according to that. So first looking at the acid, so it'd be 5 times 10 to the power of minus 3. So now I'd be taking that away because it's OH minus. So I'd be taking this away, and what I get as my acid is 4.8 times 10 to the power of minus 3 as my new acid moles. And then it would be so for my base, 0.045 plus 2 times 10 to the power of minus 4, and by that I would get 0.0452 moles of the salt. And I know that all my salts would be dissociating into the X minus, and so the ethanoate ions in this case. So what I can just do is to calculate the concentration of H plus is simply just again plug in the values. So 10, the Ka would be the same, so 10 to the power of minus 4.68. And now the new acid concentration, it'd be 4.8 times 10 to the power of minus 3. And this would be over 0.0452, and this would get me the concentration of the H plus, which would be 2.22 times 10 to the power of minus 6. Now I'm going to minus log this H plus concentration, and I get as my final answer 5.65. So if you notice, the pH has slightly increased. This is because we've added an alkali. So if we were to add an acid, the pH would just slightly decrease. Just the final bit, so the applications of buffer. So you need to know that buffer solutions keep system regulated. So especially when we're looking at reactions in living organisms. So even within humans, we require a specific pH to keep the reactions going on. And a small change in pH could be detrimental, especially if enzymes are involved. Those who do biology would know that if there's a slight pH change, then the enzymes could be denatured and there would be problems with the active sites, and the reaction may not be able to go ahead. So that's why we require the buffers to be there to keep the pH constant, so the reactions can occur. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.